Welcome students. In this advanced computational techniques course, we will discuss here about the concepts on quantum computers, nano computing technologies from microelectronics to nanoelectronics and nanoelectronics to nanoelectronics computer. We focus on quantum computers, nano computing technologies, and the transition from microelectronics to nanoelectronics, ultimately moving towards nanoelectronic computers. This topic connects physics, material science, device engineering, and computational architectures as scaling continuous, downscaling continuous. Classical computing limits push us towards quantum and nanoscale solutions. Quantum computers, basic concept of a bit and information here. In classical computing, information is stored in bits which can exist only in one of the two states at a time, such as either yes or no, true or false, or 0 or 1, on or off. In today's computer, the presence or absence of charge in a capacitor represents these logical values. However, information can also be encoded in other physical systems like the polarization of photons or electronic states of an atoms. This highlights that information is fundamentally physical and how we store it determines the limitations and possibilities of computation. Let's see about superposition and the quantum register here. Quantum mechanics introduces a completely new behavior called superposition. An atom can exist in a coherent combination of two states at once, meaning it can represent both 0 and 1 simultaneously. This has no classical equivalent. When we scale this to a register, classical bits store only one configuration at a time. But a register of 3 qubits can store all 8 possible configurations at a time. At once, all the 8 possible configurations can actually be stored. Qubits can be realized using photons, nuclei, or electrons, emphasizing that quantum hardware itself is diverse. Let's explain how exponential information capacity is working. Superposition leads to exponential scaling. 3 qubits store 8 values. 4 qubits store 16, which means in general L qubits store 2 to the power L values simultaneously. Very important here is simultaneously it can actually store all the data. Once a quantum register is initialized, we can perform operations on all these encoded values at once. For example, if qubits or atoms, precise laser pulses manipulate their electronic states. If qubits or atoms, precise laser pulses manipulate their electronic states and evolve all the values in parallel. This demonstrates why quantum computers offer fundamentally new computational power. Quantum parallelism and computational advantage we will see in the next slide. Okay. The quantum parallelism and computational advantage. In a classical system, performing a calculation 2 to the power L inputs may require 2 to the power L number of steps or 2 to the power L processors to complete simultaneously. For example, uh, uh, 10 processes there means okay, we need to actually go for a 10 number of steps, or otherwise we need to go for 10 number of processors to do it in a single step. But in quantum computer, which performs the same task on all encoded inputs in only a single computational step. This is a massive parallelism at the physical level, not simulated parallelism. This is a massive parallelism at the physical level, not simulated parallelism. The result is enormous gain in time, memory efficiency, and processing capability, opening possibilities such as cryptography breaking, molecular stimulation, optimization, and much more. Let's see here, nano computing technologies and photolithography limits. Nano computing technologies and photolithography limits. Nano computing arises because traditional lithography reaches physical limitations. Feature sizes cannot be reduced beyond roughly half of the wavelength of the light being used. And at molecular scales, doping silicon becomes unreliable, which is below 50 nanometer. Doping the silicon becomes unreliable below 50 nanometer. This actually forces exploration of for an alternative materials such as carbon nanotubes, nanowires, gold particles. It can be for organic molecules, DNA, and even biological neurons also. Unlike top-down photolithography, nanocomputers will need bottom-up self-assembly, which introduces new fabrication paradigms. From microelectronics to nanoelectronics. Electronics evolved from integrated circuits, ICs, with a few components to VLSI systems containing hundreds of millions of transistors following Moore's law. By 2008, CMOS FET technology reached 90 nanometer fabrication nodes. However, when shrinking into true nanoscale dimensions, uh, devices encounter their thermal fluctuations. Devices they found thermal fluctuations, power dissipation limits, quantum tunneling, and lithography constraints. At this scale, classical physics no longer accurately predicts behavior, and quantum effects are actually dominating. Again, at this scale, like below 50 nanometer or lesser than that, of 20, 30 nanometer, classical physics no longer accurately predicts the behavior, and quantum effects dominates. Okay, from nanoelectronics to nanoelectronics computers. This slide highlights that moving from nanoscale devices to full nanoelectronic computer architectures requires new design approaches. Moving from nanoscale devices to full nanoelectronic computer architectures need new design approaches. Future systems may integrate trillions of devices per square centimeter. Future devices may have a integration of trillion devices per within the square centimeter. Within the 1 centimeter square, we can actually, sorry, within the 1 centimeter cube, we will be actually having a trillions of devices. Okay. However, interconnections, power dissipations, and reliability challenges become the major obstacles. The architecture of integrated circuits must evolve to suit nanoelectronic components, not merely shrink existing CMOS logic. Reliability is used in nanoscale systems. See, unreliability actually arises from two major sources. First, from bottom-up assembly introduces randomness and imperfectness, meaning many devices will be actually defective. First, bottom-up assembly introduces randomness and imperfections, which means many devices will be defective. Second, at nanoscale, devices have low noise tolerance and become vulnerable to thermal noise, electromagnetic interference, and cosmic radiation. To overcome these problems, fault-tolerant schemes such as NAND multiplexing and N-molecular redundancy must be applied, allowing the nanocomputer architectures to continue functioning even when individual components fail. Even one or two individual components are actually getting failed, the entire device should not actually get failed. In order to authenticate that, the NAND multiplexing and molecular redundancy, they have to be actually applied in the new future computer. Okay. With this, we can actually stop this lecture. I hope you people can actually understand how we are actually switching from nano materials to nano electronics to nano electronic computer. Thank you, students.